believe. So I completed, or we stopped last time here. This is where I stopped. How was the quiz in general? Good?
Good.
Perfect. So let's start talking about something else, stacking. The last time we were talking about velocity analysis, determination of velocities. And during the last lab, we discussed also how we can determine velocities. The way we were doing is a manual. Nowadays, things were computerized. Everything is done through computers. So things get much easier than doing it manually. And nowadays, instead of picking things certainty with high certainty, it's better to guess. It's better to give a guess, and from the guess, we assess what is right and what's wrong. So that's how the process nowadays is. But before that, what is stacking? And why we call it stacking? The term itself, stacking, I believe, came to you before. We talked about vertical stacking, which is repeating the measurement at the same points. Here, vertical stacking or stacking, the term itself in seismic reflection is somehow different. So let's see, I got some notifications. Anything wrong? No, seems everything is good. I want to create a whiteboard to explain what exactly I mean by stacking. Send to everybody. I'm not seeing a complete list of students. So attendance is recorded as well. So stacking is basically taking measurements of the same points from different paths or from different array paths. So stacking is basically can be considered as what? Let's assume that I have one reflector. This is layer 1, layer 2. There is an interface between them, and they have many pairs of source and receiver. This is one source and receiver, that's another one. So this is the midpoint. A reflection will happen at that midpoint. There is another point, midpoint. We are imaging the same midpoint. I'm not getting new information from the subsurface. The information I receive from this configuration at least is the same. This will help me to increase the signal to noise ratio, and it will help me also to determine the velocity of the subsurface. It's one way to determine the velocity, and what we use to determine the velocity is what we call normal move-out technique. The equation of normal move-out can help us to determine what is the velocity of this layer, the second layer, and so on. And what are also their thicknesses. So if I ask how many folds I have, what is the number of fold? In this particular case, the fold is 2. There are 2 pairs of source and receiver coming from the same subsurface point. How big is this subsurface point? Is it small point, centimeter by centimeter? How big is it? It depends on something we call Fresnel zone. However, Fresnel zone, the topic of Fresnel zone will not be for the explained, at least in this course. The students who will be taking applied 1 course, they will study Fresnel zone in more detail. So that's in general what we call stacking. So to enhance the signal, we use more than 1 pair of source and receivers, and we sum them together. We get only 1 trace. The final trace is basically 1. So all of these, they will produce one trace from the subsurface point. That trace is representing the geology. How I can make this thing bigger? No problem. So all of these traces, what they produce, they will produce one trace, finally one trace. If I assume that there are more than one, the reflection or the geophysical data I record could be something like that. This is a reflection from first or nearest offset. In terms of offset, I mean the distance from source to receiver. This has the smallest offset. The offset keep increasing the farther the source from receiver is. This is the second one. That's the third one, and so on. Usually, I try to find what's the velocity. If I get the correct velocity, I can flatten them up. I can bring them straight line. Once they are straight line, I can sum them together. I will finally generate one trace. That trace is representing this subsurface point. This is exactly the subsurface point I'm imaging. So the configuration or CMP survey helps in many matters or many ways. One of them is increasing the signal to noise ratio, determining what are the velocities, and producing a better image of the subsurface. So that's how it works. We need to increase the number of pairs, but how much big we can make it? For today or nowadays, we can go up until 1,000. The fault could be 1,000. I mean that there are 1,000 pair of source and receiver, especially if we are acquiring 3D seismic data. For 3D acquisition, the fault could be very, very large. However, for 2D, the fault cannot be, probably the maximum I'm aware is probably 300 pair of source and receiver from the same subsurface point. So we talked before about stacking. Vertical stacking in seismic refraction is repeating the measurement without changing the source and receiver points or configurations. Here, stacking is totally a different thing. It's a part of seismic data processing. When we process seismic data, there are basically three main important stages. One of them is deconvolution. Deconvolution is used to remove multiples and enhance the signal too. Other one is stacking. Stacking is the second stage. Then migration. These are the three most important stages or processes in seismic data processing. So stacking is one of the most important. Among all of these three, stacking is the most important. But how it works? Simply it works like what you see here. So here, the midpoint between these source 1 up until source, for example, M, and receiver 1 up until receiver M, I asked the question, what is the number of faults? What is the number of faults, at least in this case? Anyone can answer? Any volunteers who can answer the question? What is the number of faults? How many? Yeah, 1, 2, 3, 4, 5, 6. That's correct. I have 6 different sources or pair of source and receivers. I'm getting the same reflection points, common reflection points. So I'm imaging one point in the subsurface. Are there 5 or 6? Yeah, there are 6. That's 6 different traces. In terms of data, this is my acquisition configuration. In terms of data I receive, the data will look like something to what you see here. This is the slowest or smallest offset. x1, xm is the largest offset. xm is this pair, sm to rm, that's the largest pair. And because the offset is large, the delay time or delta t, or what we call also move out, is the largest. Gets larger the larger the separation between source and receiver is. And if we predict or calculate the correct velocity, we can align it up, we can flat it up. Once we move these later arrivals, large offset traces up, we can stack them, we can sum them together. This process is called stacking. So there are different gathers. When we stack data, we should be in what we call common midpoint. This is a common midpoint gather. So such gathers, if I have a source, one point, and many receivers recording the data from this source, recording the energy, that's called common shot. These receivers are getting data from the same shot. This is called common shot. This is one shot. It could also be a common receiver, but common receiver is swapped. The source and receiver are swapped. So in case of common receiver, we have many shots and one receiver. This is a common one receiver recording from multiple sources. It does not have many applications, common receivers, except probably in migrations. This is a common offset. This pair, first and here, the first red and the first gray, the offset or the separation between source and receiver is the same for all these pairs. What you see here is what we call a common midpoint. This is a common midpoint. The smallest separation is where the source and receiver are exactly in the same point. That's zero offset. The largest offset is between what you see, the first red point and the last gray point. In terms of data, we receive such data, and it's hard actually to determine what was the gather type. Was it common shot, a common midpoint, a common receiver? It's really hard to determine the gather type looking into the data. So someone might ask, how I can tell what type of gather is it? You can't easily tell, unless if you know how the data were acquired in the field. So you need to know what are the trace headers, or what we call the associated location information for each trace. So traces, usually it's a wiggle, a wiggle, but it has other information. What is, for example, its location? What is XY location? These information are always associated with traces. If they are not associated with the traces, you cannot use the data. You cannot do anything with this data. You cannot process the data unless you know what was the XY location of the source, XY location of the receiver, what is the distance between them. These are always usually associated with survey configurations. Whenever they do the survey, they attach these informations to each trace and source locations. So let's take a good example, a quick example, how it works in practice. So here is a vessel or a ship, and it has a source, and the vessel is tied to what we call a streamer. A streamer contains hydrophones. So in this simple configuration, I can see 3 center hydrophones. That's one receiver, another receiver, third receiver. It can contain more than 4 or 3. So it has 1, 2, 3, 4. Let's consider the midpoint. Since I'm only seeing 3 receivers, here the shot have happened. See the pointer? Here the shot has happened. This one will receive, this geophone or this hydrophone will receive energy from 2 different reflectors. First reflector, the second reflector. 2 different reflectors. And based on Fermat principle, we say that the energy takes the shortest path between source and receiver. This is the shortest path for the reflection, because the angle of incident and the angle of reflection should be the same, or must be the same, for at least the reflection, seismic reflection energy. So the trace I record, or the trace the geophone or hydrophone actually records here, is the red one. Is the one you see as a red. This gather, do you think what kind of gather is this? The one you see here. Is it common shot, common receiver, common offset? What kind of gather is this? I'm waiting an answer. What do you think? Gather type, what we see here. It's a gather. What kind of gather is that? Any volunteers who can answer? Let's go back. Is it common shot, common receiver, common offset? Perfect. Yeah, that's true. This is a common shot. One shot, multiple receivers. One shot, one source point, and multiple receivers. That's what we see is a common shot. That's a common shot. Where is the middle point? Or at least here, that's the middle point. This is the subsurface point we imaged, at least this first hydrophone image. The others will record also data. This trace is coming from the second hydrophone. The third, the last trace is recorded by the last hydrophone. Then what happens? The ship will move some distance. And that's what we call source offset. The ship will move some distance. And right now, the midpoint, that midpoint is imaged by the second geophone. The offset is larger. This midpoint is imaged by the second hydrophone. So the offset between first geophone and the source for this midpoint is smaller, whereas the midpoint gets larger. I'm still imaging the middle point. I record a shot gather. This is a second shot gather. And the offset for the second hydrophone is larger, the red one you see. I'm still imaging the same midpoint. That's the same midpoint. And the next time, the vessel will move again a certain distance. That's what we call a shot distance or shot increment. Right now, the middle point, this one is recorded by the last hydrophone. The last hydrophone is recording the same midpoint. So what's active right now from at least this midpoint is this trace. First trace, second trace, third trace. So what I do, I have this data. I have 3 different shot gathers. I need to sort this data to change the gathers and only take from those gathers the traces belonging to this specific midpoint, specific point in the subsurface. So from the first gather, I take first trace. from the second gather, this data, this is a gather, common shot gather, as you said. I take the second trace, and from the third gather, I take the third trace. And I can plot them. I plot them in a different configuration. I plot them as common midpoints. I plot them as what I say common midpoint. So this trace, the second trace in the second shot gather, 1, 2, 3, they have the same midpoint. I can call them common midpoint. I combine them together. I bring them 1, 2 goes here, 3 goes here. This trace goes here. So I form what I call, so what kind of gather is this? What do you think? What kind of gather is this here? No, not common offset. It's not a common offset. It's a different gather. That's a common midpoint. They have these, came here. This trace, the red, came here. This one came here. They have the same midpoint. They have the same midpoint. This is basically the distance from the source. This distance, the x-axis is the distance from the source. How much distance is from the source? How much distance from the source? So what I see, the far offset, the NMO, normal move out, or delta T is larger. And how I can correct it? I need to pick the right velocity. Because the time difference between, this is the time difference between T naught, T at 0 offset, there is 0 offset, and any other offset. It follows the equation of hyperbola. I know the x, I know what is the x, how much distance between this, what they call a trace and a shot. But the only thing I need to determine is the velocity. And how we determine the velocity, it's based on the lab we did, or the lab I gave you. Probably you are still working on the lab. It has been discussed in the previous slides, the last time when we met. So if you pick the right velocity, you can easily flat the line or reflection line. So let me see someone speaking or knocking the door. Sorry, I have lecture. When I close it, don't open. I have a meeting. Okay, thank you. When you see it's closed, don't. Okay, no problem. Thank you very much. Sorry about that. I keep knocking the door. That has been like that for almost 1 minute. So what I do, I pick the right velocities. If my velocity is larger than the correct velocity, I will get what I call that kind of flattening. I undercorrect. If my velocity is larger than the true velocity, I undercorrect. If my velocity is lower than the true velocity, I overcorrect. So if you have this equation, that's the equation of hyperbola. How you can equate these two? How you try to find, you need to find this term. You need to find exactly what is this term. So this term, I already know the x. The x is basically this distance. However, I don't know what is the velocity of the subsurface. That's something I need to determine. So the question, why when the velocity is larger than the true velocity, I say it's undercorrected. Whereas if the velocity is lower than the true velocity, that's the true velocity. If it's lower than the true velocity, I mean it's overcorrected. I say it's overcorrected. What's the reason behind that? The reason is apparent or clear from the equation itself. So I need to remove this value. I need to subtract this term, x squared over v1 squared. So how I can subtract it? I need to find it, what's the value. I can remove it from both sides. If I remove this one from both sides, t at any offset will become similar to t at 0 offset. So if this velocity is larger than the true velocity, if the velocity I calculated or guessed is larger than the true velocity, this term gonna be smaller. This term is smaller. So when I subtract it, I get a lower t. I get a lower t. That's what's exactly happening. Then that's the reason I call it undercorrected. If the velocity is lower than the true velocity, when I'm applying normal correction, normal move out correction, I'm trying to flatten my reflectors and stack them together. If the velocity is higher than the true velocity, I say it's undercorrected. Whereas if the velocity is lower than the true velocity, I say it's overcorrected. When the velocity is, when you guess the true velocity or calculated the true velocity, the traces will line up exactly, and you can sum them together. You can average them to one trace. This is the trace I'm calculating exactly from this subsurface point. So this is the process of CMP survey or normal move-out correction. After this process, we move from what we call gathers, different gathers, shot gathers or common midpoint gathers. They are not seismic data. They are not seismic, they are seismic data, but they are not reflection data, or what we call, I cannot use them to interpret the geology. Usually the geology is interpreted after you stack your data, after you get only one trace resembling one subsurface point. That's what we call stacking. That's how stacking works. So since it's not an easy process to determine the velocities, usually we make guesses. We guess a lot of velocities. So at least in this example, the true velocity is 1700 or 1700. How I can determine it? It's hard. It's not easy, especially if you have a lot of gathers. So the best thing is to guess it. And I guess a lot of velocities, not one velocity. I provide a lot of different velocities and observe which velocity will perfectly align my traces. Probably I test velocities from 0 up until 6,000 meters per second. I test all these velocities and check what velocity will flatten my reflectors. So this is exactly what's happening. So this is upside down, basically. This is a reflector. It's just being upside down. If I combine them or align them at line 1 or curve 1, that's the amplitude I receive. If I align them and merge them or stack them at curve 1, this is the amplitude I receive. If I align them exactly at curve 2, I get a maximum power. Whereas the same is true for, 1 and 3 are comparable. If you align them at 3, you will get a lower power. The peak power, if you align them exactly at a line or curve 2. What are these lines? These are different velocities I'm calculating. These are different curves. So this is a real data. These are hyperbolic curves. Each of these hyperbolic curves represent a different velocity. This is one velocity, another velocity, another velocity. I test all these velocities. I check which velocity, which of these 3 velocity will give me the maximum power or maximum peak. It's apparent, at least from this case, that the curve or curve number 2 will give me the maximum peak. This is a guessing game. You just keep guessing until you get the maximum power. But usually it's not done the way we make it in here. We do something called semblance analysis. With semblance analysis, so this is a CMP gather. What you see is a CMP gather. There are different races. Race 1 up until the last race. And I see different type of energy. That's the direct probably. This is a refraction. That's a refraction. Then I see a lot of reflections. These are hyperbolas. Those are different hyperbolas. 1, 2, and so on. So what I do, I test a lot of velocities. First of all, I choose, for example, velocity of 500. I apply a velocity of 500 to all of them. And I stack them. And then I choose a velocity with an increment. So first one was 500, the second one going to be 600, 700, and so on, with an increment of 100 between one tested velocity and the next. So when I choose, for example, at least in this case, they started from 1,000 up until 6,000. The starting velocity they start testing from is 1,000. The final velocity is 6,000. They are testing many velocities. And they are generating lines similar to what you see here. These are what we call semblance analysis. So for example, a velocity of 1,500, a velocity of 1,500 or 1,500, this will exactly flatten this curve, first curve, will get flattened exactly. Whereas the next, the lower one, because we believe the velocity will increase as we go deeper, there will be what? Overcorrected. All the rest will be overcorrected. The next reflector will be something like that. This will be something like that, and so on. They are overcorrected, similar to what you see here. I use the lower velocity, so they have been overcorrected. Every other reflector will be overcorrected. The only one which be flattened perfectly is the first one, because probably that's the correct velocity for this reflector. The deeper one will be overcorrected. Overcorrected. I'm using a lower velocity. So for this specific velocity, if I plot this semblance, this is the semblance. If I plot this semblance, so the semblance, what I see, there is time and there is also velocity. Time versus velocity. So I have a time, this is time axis, and this is the velocity axis. So the semblance will look something like that. At least this one, maximum power here. Let's use another color so you see what's the color difference between them. The semblance will look something like that. Maximum power here. That's the reason you see it black. That's the reason you see here it's black. Means this reflector perfectly flattened for velocity of 1,500. It's exactly flattened. So when I sum them up with this specific velocity, I got the maximum power here. Whereas for deeper one, because I believe the velocity increases as I go deeper, they will be perfectly flattened for higher velocities, probably a velocity of, let's say, 300 or 3,200. That's the velocity here. 3,200 probably. So this reflector will get flattened if I use a velocity of 3,200. And when I stack them together, it will perfectly produce for me the maximum power. So that's the image you see behind, that's the semblance. You then, as a geophysicist or seismic processor, your task is to pick this line. You see this plus signs? That's your picking. The computer can pick them for you if you use advanced techniques, but still up to know the interpreter picks the best velocities. So the person who is doing seismic processing, he will pick the right velocity. He thinks that since this is the darkest point, the energy here is the largest. I picked, or the velocity which aligns this reflector is exactly, as I said, 1,500. So I pick this velocity. Then I make another pick here and another pick here. I make a lot of picks to make the line. You see this line? I'm not sure why it's going erratic, something like that. So this is the line. I try to draw the line so it goes to the maximum power. If you select this line, if you draw these points to make the line crosses this maximum power, what you produce, you will produce reflectors which are flattened. They are flattened right now. And once they are flattened, what is the next step after flattening these reflectors? Who thinks what is the next step? After this step, what is the next step you think, according to your understanding? I just explained that. Any volunteers? What do you think? What I can do after flattening the reflectors? Perfect, sum them, stack them. The next step is just stack them. They all will produce only one trace. So there is probably, if I count them, maybe 30, 35 traces. Those traces are from the same subsurface point. As Aisha said, we just stack them, we sum them together. We produce one trace. That's the process of CMP stacking. So the next lab, you will do something similar to this. You try to pick velocities using some computer techniques. And you see that exactly whenever you are picking the right velocity, the reflector will be flattened exactly. You use a lower velocity. If you make, for example, let's assume that my picking is here. Instead of picking here, I pick here. So what happens? This is a lower velocity than the correct velocity. This is the correct velocity, but instead I picked here. What happens to this reflector here? It will be overcorrected. This one will go up. If I choose, for example, another one here, this one, if I choose a velocity instead of here, I pick somewhere here. So it goes, the line goes something like that. Something like that. Instead of the correct velocity here, I pick somewhere here. So I undercorrected. This line will be something like that. This has been undercorrected. That's what I mean by overcorrection or undercorrection. You need to pick the correct velocity. And believe me, this semblance is really good. Sometimes you get very poor. You cannot decide where exactly should I pick, because the power can appear everywhere. Instead of one power here, one black dot, here you see some dots here or here or here. And it's not easy to know which one is the correct one. A quick question. I believe a smart person can answer this question. What if you see a similar black dot probably here? What that could be? What could this be? But if I see a black dot here, you see these black dots behind, those plus signs? Those are maximum powers. What could be a black dot here? Yeah, it's a noise, but what kind of noise? That's true. Perfect, Rachel. That's a multiple. Amazing. Yeah, that's a multiple. This is a multiple, because what happens if I have a data like that? So this is the primary. So the primary might appear here. That's the primary. The multiple goes 2 times. Double the time. So the primary probably is here. This is the double time. 1, 2. Since it's still traveling in the same layer, it's not going deeper, it's still the same layer. It means this velocity, instead of here, it could be here. Yeah. Let's make it clearer. So let's say it's here. So these and this velocity are the same. It means this reflector here, this reflector, it had also a multiple here. This is the multiple. This multiple produced for me this peak. That's really amazing. Someone could answer these things. It means you understand the course perfectly. So this is a multiple. The multiple appear like that. It's a good way also. CMP stacking is a good way even not to remove only the non-coherent or random noises. They also remove part of coherent noise. Multiple is a coherent noise. CMP stacking can remove some coherent noises. Multiple can be removed. It's a good thing. So let's discuss something more advanced. Up until now, we were talking about flat dipping layers. But usually geology is much more complex, and we could have layers which are dipping actually, or having different structures, syncline, anticline, and so on. For dipping reflectors, the things usually much more complicated. And what we receive is not the true dip. It's an image of the up dip. So if this is the true dipping, let's assume that this is the true dipping. Your reflectors will appear something like that, or traces. That's first trace, second trace. Okay, I'm not sure what's going on. Let me take a screenshot. So this is bad. I removed every what I call editors, or so the reflector will appear something like that. Here is the second one. That's the third one. Ignore those peaks. I'm not sure why they're happening. So I have the reflectors here, which is not true. They're appearing up deep because the reflection, as we said, takes the shortest path. And the shortest path between this source and receiver pair here, the source and receiver at the same point, is the perpendicular line. So what will appear to me if I connect a line joining these reflectors, it appears to me that this is the true reflection, which is not true. How I can correct? It's not easy. Usually the correction is done through a process called migration. We talked about 3 different processes in seismic data processing. First is what we call the deconvolution, then stacking, and finally migration. But the simplest way to image it, you take a protector, فرجال, and try to draw a curve from this interface, from these reflectors. So I draw 3 curves because I have 3 different traces. You cannot determine the dipping using only one pair of source and receiver. You need to have a lot of pairs of source and receivers. So that's what you do. And try to draw a line, then going or attaching all these 3 circles. This is one circle, another circle, and there are 3 different circles. The line which attaches or go tangent to all these 3 circles is this line. That's the true dip. And this is how migration works usually. Behind the screen, it's a complex mathematical formula, but this is how it works. In general, if there is a dipping, the reflection will appear up deep. So this is the true layer, whereas your reflection will appear up deep, and it will appear gentler. To correct it, you need to do migration. You need to do migrations. So for dipping layers, I will see the curve or apex of this hyperbola shifted to the up dip direction. This is the up dip directions. So it has been shifted from where the source receiver midpoint is. That's the source receiver midpoint. It has been shifted some distance. This is the X. And we can calculate then, this is supposed to be the minimum of the 0 or 0 offset time supposed to be here. It will appear a bit lower. And you can calculate 0 offset for dipping layers using this equation. So without dipping, T naught is how much? Is 2H over B. With dipping, it's gonna be multiplied by cos of the dipping, cosine of the dip amount. Yeah, it's not easy to calculate because we don't know what's the dipping. Usually we can't tell what is exactly the dipping of the subsurface layers. So there are advanced processes. I will not touch them in this course. What about the offset? This distance, how much this distance moved from the original or assumed zero offset. This is the zero offset because the center of source and receiver will lie here. I have source and receivers, their centers will lie here. It will be calculated as such, 2h sine alpha. So let's move because we'll discuss much more detail. We know that in terms of geology, the layers are not usually dipping. They have many different geologic features. We know that this is an anticline, this is a syncline, this is a monocline. And what you see in this cross section is, what do you think is that? What is that? Anticline or syncline? That's an anticline. This is what you see here is a syncline, big syncline. This is a series of anticlines and synclines. It's highly folded structure and it's dipping slightly. What we name a fold which is horizontal, what we call such fold? Not overtoned. They call it something else. They call it recumbent. Haven't you studied geology, structural geology, or even geology too? They call these kind of folds which are horizontal, we call them recumbent. That's true. This is a recumbent fold. So how they will appear in seismic sections? That's the interesting thing. That's what we want to know. So if we have a syncline, a tight syncline, where its center is below the subsurface. So in this case, this is a syncline. Its center, or the center of the curvature, is below the subsurface. And we assume that there we have a source and receiver. The energy goes, reflects back. This is the zero offsets. And in normal move out, we are removing everything or moving everything to zero offset. We are removing the part where the offset between source and receiver is non-zero. Seismic sections, they are all moved to zero offset sections. So this is a source and receiver. There are 3 points where this energy perpendicularly hit the interface. 1, 2, 3. There are 3 different points. All these points can generate energy. If there is a source and receiver in the same exact point here, the receiver will get or receive 3 different wiggles. So it's hard to determine from where this wiggle came. Let's take an example, a real example. This is in terms of geology. That's the depth domain. I have a source and receiver here. At number 1, I have a source and receiver. This is one possibility. The energy goes directly down and reflect back when the interface is perpendicular to the energy itself, to the incident angle. That's one. This is another one. Here it's also perpendicular. This is as well another one. Here. So I receive 3 different reflections at source receiver pair 1. So this is a zero offset. That's a zero offset where the source and receiver are at the same points. I receive 3 different reflections. The energy goes something like that. Another one, another one. 3 different reflections. My question, first reflection, from where is it coming? It's coming from this energy going down and returning back. It's 1. The second one is 1B. That's shorter distance than 1A. So I get 3 different reflections. And at number 2, the same applies. Number 3, again, the same, and so on. So in time section, after stacking the data, you will receive something like that, such structure, which is totally different than the structure we see here, the geologic structure. It's not in any way close to this real section I see. That's the real section. So synclines, this is a syncline, a geologic syncline, will appear as what we call bow tie. This is a bow tie in time section, in seismic section. This is a geologic section, whereas this is stacked seismic section. They will look like exactly what we call a bow tie. Have you heard of bow tie? What's a bow tie? Bow tie, ربطة العنق. They name it bow tie. So this feature, what you see here, resembles a bow tie. This is close to a bow tie. So how we can remove it? Again, migration can remove it. What is the takeaway? What you need to know from all this? You need to know that whenever we have a syncline and the center of curvature of this syncline is below the subsurface, it's very tight syncline, it will produce a bow tie feature in seismic sections. This is a seismic section after stacking it, after the anomaly correction and stacking. Anomaly correction is flattening the reflections. Stacking is summing them together. So this is a stacked section. In the stacked sections, we see that syncline, tight syncline, will look like as bow features. What if the syncline is very broad? They will not look like synclines. If the syncline is very broad, let's assume it's something like that. So this syncline has its center of curvature above the surface. This is in geologic section, geology, that's depth. In seismic section, it will look like a broader feature. It will appear very broader, wide open. And how we correct that again? What process we use? We use a process called migration. Do you need to know how we migrate exactly? No, at least in this course. We don't need to know what migration process exactly is. What about anticlines? How they look like in seismic sections? So if I have an anticline, this is an anticline. That's what I will see. In some places, for example here, I will receive 2 different reflections. So here, this is the trace. It will appear something like that. I believe I need to make it quick. I received 2 different. In this case, also I received 2. So here I receive 1 2. And that's how it appears. 1, 2. 2 different traces. Here I will receive only 1 reflections. So here I will receive 1. This is what you see in case of anticline. In seismic section, you see such a feature. It's a weird feature. It's not truly an anticline. How to correct for that? Again, what do you think? What's the process we use to correct for anticlines? We use again migration. That's true. We use the migration technique. So migration is a process that it corrects for many geometric artifacts or anticlines, synclines, dipping. They will all be corrected using migration techniques. Migration is extremely complicated process. And migration nowadays are not only applied in stack section, we can even do migration before stacking. But those are much more complex. So let's see some examples of migration and unmigrated sections. But before that, let's discuss what we call diffraction. What is a diffraction? Any irregularity in the subsurface. For example, a point scatter, a cavity, a pipeline, a fault tip, all these can generate what we call diffractions. Diffractions generate energy similar to what we call hyperbolars. So diffraction cannot easily be distinguished between from reflections, rare reflections. So here is a point. That's a point. This point could be a cavity, a pipeline, whatever in the geologic section. If the energy hits this one, the energy emits in all directions, following what we call Huygens principle. So based on Huygens principles, the energy at this irregularity will move in every direction. So if there is a source or receiver here, this receiver will receive the energy from this diffraction as well. So in time sections, because this path is larger, here is a receiver, it will record the reflected energy at later time. And this is a little bit shallower time, and so on. If you connect those lines, you will generate a curve similar to what we call a hyperbolic curve. So in this section, all of this energy you see, there are diffractions. It means that in geologic sections, there were a lot of irregularities, a lot of point sources. And the way to correct diffraction is also through migration. The migration can do a lot of things. This is the final seismic section. It's not interpretable at all because it has a lot of diffraction energy. We need to apply what we call migration. And those diffraction happens for many reasons. Pinch outs, point sources, usually maybe pipeline, maybe a cavity, faragh fil ard. Pinch outs in geology, we say that this is a pinch out. This is a different rock layer, which is closing or ending at one end. That's what we call a pinch out. This point here will act as a source or a point diffracting energy in every direction. Faults, this is a faults. In faults, that's a fault. How many points do you think will generate diffractions? How many points are there which can generate diffractions? This is a fault. where diffraction can happen. How many points that can generate diffracted energy? If I have a faulted layer. Any answers? Maybe one. This is one, and this is another one. Yes, that's true. These 2 points can generate diffractions. These are breaks in the reflector is not continuous, so it can generate diffracted energy. So let's see some examples of them. That's a point source. It's in geologic sections. The energy goes when it hits these points. It could be a cavity, فراغ في الأرض. The energy goes in every direction. That's how you see it. It goes even down, but this ray path is larger or longer, so the trace or the energy received from at this receiver will appear deeper in time section. It appears something like that. So it forms what we call a hyperbola. That's the hyperbola in time section, in two-way time section. And once you apply migration, this energy collapses back. It go back to 1 point. So all these traces gonna be straight lines. Only one trace will have a pulse, this trace. The rest are all straight lines. Ignore this peak here or this spike. That's how it appears after migration. This is after applying migration. So here I have stacked section. This is time axis, two-way time. If this is a diffracted energy, we apply migration. After migration, what you see, that's what you see. Similar to what you have seen here. So all those energies were collapsed back to the point from which they were generating. This is in geologic section, or sorry, in time section, in seismic section. In geologic section, that could be anything. This is a depth. This could be, for example, let's say a cavity. This is a cavity that generates energy moving in every direction. So as I said, for a fault, this is a fault. The fault will show up 2 points of diffraction, the upper side and the lower side. And they will receive 2 diffraction lines or diffraction hyperbolas. Again, how to remove them? The process is migration. Here is a section. What do you think are there? What do you see geologically? What do you see geologically in this section? Faults, that's true. Exactly. They are not clear, but still I can see faults. So this is a layer. That's another layer. I don't see the layers are continuous because it has been faulted. So this one here is probably here. You see how much moved? It moved so much. And so on. This is before migration because I'm already seeing this energy. Do you see this energy here? These are diffraction energy. This is also a diffraction energy. These are all diffraction energy moving like that. How I can remove them? I apply migration. So in the migrated section, I remove my drawing, compare between the two. This is much clearer. If I ask you where to draw the fault, you might have mistaken or made the drawing poor. Whereas here, I can easily trace the fault line. That's the fault line. Ignore these peaks. This is one fault, another fault. There are two faults I see in this section. This is after migration. So there is a large improvement after applying migration. Side to side, before migration, after migration. Those are two stacked sections. Here, this is stacked section. After stacking, after applying in a more correction and summing the traces from the same midpoint. What kind of features you see? What do you see here? Anticlimates. Yeah, that's true. Because there are, this is a bow tie. This is a bow tie. This is also a bow tie. You see here, this is a bow tie. Two different bow ties. These are anticlimates. And after applying migration, let's apply migration. You see big difference between these two sections. That's after applying migrations. So migration is a complex process, and it's easily recognized that whether the section have been migrated or not. And sometimes they keep the data unmigrated. Some reasons to save, for example, the money, because migration is very expensive process. It takes month and month. There are dedicated processing companies. PDU, for example, PDU itself does not do processing, does not do seismic data processing. They hand over their data to another contractor company, and the contractor company, they process the data. They apply migrations. And they hand over back the data after migration. So it might take them 2 months, 3 months, probably sometimes even years to process the data. Especially some techniques of migration. Migration is a lot. There are a lot of techniques of migration. Some of them, they are very, very time consuming, computer intensive. It takes a lot of time. To save time, probably you say, oh, just give me the data as stack. Bring me the data as stack. Let's have a quick look to the data without going through the process of migration. And you can easily determine whether migration is necessary or not. For such data, for example, what you see here, migration is certainly important. Cannot skip the process of migration. So 5 minutes left. There are few slides remaining. We will complete next time. For the time being, I would like to ask you whether you have any questions related to what we have discussed so far. Any questions? If you go to the end of these slides, yes, Ammar. Ammar has a question. What's your question, Ammar? If you can't say what's your question, you can talk. Unless if you don't have a mic. So if you go to the end of this slide, what generate diffractions? We'll come back to you. This is the reading part. Here you need to read. There is a section about seismic sequence stratigraphy. Seismic sequence stratigraphy. This is not covered in this book because it's a bit advanced. So what generate diffractions? Diffractions happens because of what we call Huygens principle. Huygens states that any point in the subsurface will act as a source of energy. So considering Huygens principle, fault does not create diffractions. Faults create because there are hard breaks. In folds, there is no hard break. So cavities can generate diffractions. Folds can create diffractions. Pinch outs, this is a pinch out. In geologic section, that's a pinch out. That can create pipeline. If there is a pipe, this pipeline will generate diffractions. All such irregularities in the subsurface will generate diffractions. Cavity is even a different rock. For example, there is a different rock fragments than the surrounding. This rock fragment can generate diffractions. And why it happens? It happens because as Huygens states, energy, every point generates energy, and they might interfere or interfere destructively or combine together. They enhance together. Whereas in these points, they will not ever. These points will generate energy, diffraction energy, following Huygens principle. The energy generated from these points will not interfere destructively. They will interfere constructively. So what I see, a diffraction energy in a diffracted energy in two-way time in seismic sections. This is a depth. This is in geologic section, whereas this is a seismic section. Here, the energy, these points, because there is no irregularity, this point is also generating energy in each direction. But the energy generated at this point will somehow interfere destructively from the energy here or energy here. Whereas the energy at those points, irregularities, they will interfere constructively, generating for us what we call diffracted hyperbolas. They have the same shape as reflections, as primaries. So they are not easily distinguishable. Migration can remove them. So I close now because I exceeded my time. Welcome. First of all, let me stop the recording.